Okay. Non-parametric statistics are a special class of hypothesis tests. So they're basically used when the assumptions for parametric tests are not being met. So again, the assumptions for parametric tests, remember them, it's independent samples, random sample, normality, homoscedasticity, and linearity. So there needs to be a linear relationship which you can establish in parametric tests. It really distinguishes a pattern here in chance when the observational data is not a scale-dependent variable. So if you have a scale-dependent and a scale-independent variable, that association is basically a linear equation, a linear fit through all individual data points. So if you have a categorical variable, you cannot do that because the differences between an independent variable that is categorized are basically not reflecting the magnitude of whatever numerical value you would assume. So it allows you to capture these patterns and associations between observational data where you do not have scale-dependent variables. So what are you essentially doing? Essentially, you mean to pick up patterns that are deviating based on the observed data, deviating from what you would expect. Let's assume a use case where you're basically testing, and from my world, from medical testing, this is quite a common scenario where you have categorical data. You have somebody is COVID positive compared to COVID negative, and you have a test that gives you a positive result or a negative result. So that's basically a typical use case. You have a 2x2 table where you have COVID positive and COVID negative, and you have test positive, test negative. So when you would assume this null hypothesis of this being not associated, there would be an equal distribution in each of these cells. One simple example, only you want to compare the proportion of patients that test positive for COVID on Monday compared to patients that test positive on Tuesday. The equal distribution, where there's no association between weekday and testing positive, would be that you have 50% of your patients being on Monday and 50 on Tuesday. So at the end of the day, you're comparing counts, but in the end of the day, you are comparing the probability of a condition being met or not. So this association we're gonna essentially investigate today. So in the simplest format, you have only one level of that nominal variable. In a more sophisticated case, you can have 2x2 tables, you can have 3x6 tables, you can have so-called contingency tables for a number of various levels of dependent and independent variable. And the chi-square will give you as your null hypothesis or alternative hypothesis, essentially an indication whether there's an association between the dependent and the independent variable. And this association, you can then formally test, quantifying the probabilities of being in either category. And we will do that as well by calculating the relative risk. Okay, so that's the summary I've given before. So we had an independent variable that was scaled and a dependent variable that was scaled. That is where we think of correlation and regression analysis. Correlation basically quantifying the association and the strength of association between two scale variables, with regression basically carrying correlation further and allowing by development of the regression function to basically predict the dependent variable based on numeric values of the independent variable. The nominal independent variable and scale dependent variable is tested with a STAT test, for example, where we have sample mean versus population mean, knowing the standard deviation from the population, all kinds of t-tests, single sample dependent, independent sample t-test, and all kinds of ANOVA, where we have a nominal independent variable at 3 or more levels. So now we have nominal independent and nominal dependent variable. So that basically, it's either nominal or ordinal. You can use them for either use case. So keep in mind, nominal is basically a named category, whereas an ordinal variable is a variable that essentially has some order in some shape or form contained in its information. You can also use non-parametric tests when the sample size is small and the underlying population is not normal. You can, so there are more sophisticated tests than that. So there's a Wilcoxon signed rank test, and there's a Mann-Whitney U test to do a formal testing. We're not going to do that. We're just going to do chi-squared. But just to put this in perspective, if you have data that is either relating to each other, whether dependent on the independent variable is in a nonlinear relationship, or it's non-normally distributed, you can also approach this in a shape or form with a chi-square by basically stratifying your variables in, for example, tertiles or quartiles, which basically are equal parts of your population. So basically you're cutting this down into 4 equal parts, as we have done with the 25th, 50th median, or 75th percentile. You cut this in 4 equal parts, and you basically can sense for associations also using a chi-squared, hypothetically. It's not as insightful, but it's possible. So these are the use cases when you use non-parametric tests. It has some limitations. So since it's non-normally distributed, you have problems computing confidence intervals and effect sizes. Particular confidence intervals are quite tricky because they're logically not symmetric, because it's basically skewed in one direction over the other. Effect size measure are also quite difficult to compute, and usually these computations are resorted to statistical softwares. Of note is also that non-parametric tests are more likely to give you results with less statistical power. Consequently, you will always try to prefer parametric tests, but parametric tests are also more conservative. That means you may hypothetically always try both in case you're opting for a non-parametric test first. So consequently, to a smaller statistical power, you also have a higher risk of a type 1 error. Keep in mind what type 1 and type 2 error is. So the type 2 error, if you have a null hypothesis that is not true, you either are rejecting it or you're not rejecting it. If you're rejecting it and the null hypothesis is indeed not true, you make the correct decision. That is your statistical power. If you're not rejecting it, although you should have rejected it, this is a type 2 error. And the total of either making a decision in favor of the null hypothesis or against the null hypothesis, this probability adds up to 100%. So type 2 error and statistical power adds up to 100% probability. So keep in mind, there was, when we talked about effect sizes, there was a 2-by-2 table, null hypothesis true versus null hypothesis not true, and there was the categorization in the type 1 and type 2 error and correct decisions. So type 2 error, you're not rejecting what you should have rejected. Type 1 error, you rejected something you shouldn't have rejected. So with the chi-square test, you basically distinguish 2 different chi-squared tests. The first is the goodness of fit, where you have 1 nominal variable. But this is the example of the weekday. How many did you test on Monday? How many did you test on Tuesday? If you don't see any association between weekday and probability of COVID positive patients, you would basically compare this with a goodness of fit chi-squared. If you have 2 nominal variables, then you're basically testing for a chi-squared test of independence to test your null hypothesis. And this is an example that we will do today, but we get to that later. So there are 2 examples today. Both are basically testing both chi-square. The goodness of fit is rather a quick one. But you have an Excel spreadsheet on your canvas that will allow you to follow along or to play around at home. So you basically, so it's labeled module 22 calculations. And the first example is a little bit of more esoteric research that was conducted on elite youth players in Germany. So the researchers came up with the hypothesis that boys that start playing soccer and were born in the earlier years of the year, the earlier months of the year, are more likely to become elite youth players as compared to those born in the end of the year. They were trying, and you can read the example up in the book, it's like they were trying to kind of establish some causality in regards to light exposure time of the mother, and I don't know what not. But hypothetically, they tested for whether elite youth players are more likely to be born early in the year. So essentially what you need to do first, you need to kind of operationalize what you have given. So you basically, you have two different cohorts that you're testing. You have those elite youth players, soccer players that were born in January, February, and March. Then you had those that were born in October, November, and December. The difference here is 52 that were born early in the year compared to 4 that were born late in the year. So that's defining the levels of your categorical variables. So you basically have early in the year and late in the year. And then you have an observed count. And that's basically written here. So you have 52 in January, February, March, and you have 4 in October, November, December. That's all you need to do for the goodness of fit. And then you need to do some simple set calculations. But basically that's already meeting point number 1, step number 1 of your hypothesis testing. So you identify your populations, you identify your distributions, which you know it's a distribution as per count, and the assumptions. Well, you state the hypothesis. What's your hypothesis? The null hypothesis would be that there's no difference between the two levels of the independent variable. And that would essentially also give you kind of your idea what the null hypothesis would look like. So if there were no difference, there should be an equal balance of youth soccer players early in the year, born early in the year, and born late in the year. And we will test whether this is statistically true. Then you determine the characteristic of the comparison distribution, you determine critical values, you calculate and decide. Same concept. With the goodness of fit, you always have two populations of your nominal variables. So they basically stratify. There's two levels of your nominal variable. Stratify your population in two parts. And you're basically matching those frequency in those two levels, which we have done here with 52 and 4. And now we need something which is which goes along with the null hypothesis. So we need an expected count. So if you would not assume that there's a difference between early and late, you would have an expected count of 50-50, right? So you have a total of 56 individuals, 56 soccer players. If they were not different in terms of when they were born in the course of the year, there would be 56 divided by 2, and there would be 28 in each group, right? Then we would assume there's no association with time of the year. So this basically is your observed and expected, and that's the core piece of your calculation of the chi-squared. And you basically have a comparison distribution, which is the so-called chi-squared distribution. And you have a chi-squared table on your canvas, which I highly recommend you're going to save somewhere that you have it accessible for the quiz. So you have here, again, just like the ANOVA, the F statistic, the F distribution, you have a unimodal right-skewed distribution with a critical value that corresponds with the degrees of freedom. So meaning if you have a degree of freedom of 6 and you're testing against an alpha of 5%, your chi-squared is 12.959. So that's how you would read that. So this is your comparison distribution. You have then the assumptions to be met. So they're both nominal, or it's just one variable, 2 levels. It's one nominal variable. they're independent observations. So this is important. They're meant to be independent from each other so that you don't double count into your contingency table. Then you have random selection, which is likely not the case with your elites use soccer players. And you have a minimum number of expected participants per cell. There should be no zero in there, and hypothetically, none of these cells should be smaller than the number of individuals. The number of counts should not be less than the number of cells in your table. So based on that, you would then quantify your degrees of freedom. So you have degrees of freedom for the row. That means a row would basically, the number of rows minus 1 gives you the degrees of freedom. The degrees of freedom for column is the number of columns minus 1. And the degrees of freedom for chi-squared is df row multiplied by df column. So that gives you the df chi-squared. For goodness of fit, it's always 1. So for this table, we would assume the degrees of freedom to be 1. For others that are larger than just 2 levels of an independent variable, of an independent nominal variable, this would be 1. So here we have an excerpt of a chi-squared test. What is the interesting aspect? So the one that I shared with you doesn't have degrees of freedom of 1, so it doesn't account for a goodness of fit test. Here we do have that degree of freedom of 1, and we see the alpha level of 5% represented with a cutoff value of 3.841. So this is the degrees of freedom we need for our soccer players. So if we now enter our cutoff value, our cutoff chi-square is 3.841. So the comparison distribution with chi-squared was a cutoff value of 3.841 on a p level or an alpha of 5%. So now how to calculate the test statistic? And this is where things getting a little trickier. So let's copy this over. It's not as complicated as it looks at the first glimpse. So we are interested in calculating chi-squared. So we know this is the sum sign. So we know observed are given from our example, from our count. Expected, we calculated as the counts, the overall count, evenly distributed amongst all levels of the nominal variable. So observed minus expected squared divided by the respective expected count for each of our levels will give us each component of that sum that we need to build, and summing all of this up will basically provide us with a chi-squared. So that's as simple as it could be. So we only have to calculate now O minus E, which is observed minus expected, which is observed minus expected, that's 24. And doing the same with late gives us minus 24. So now O minus E squared is now this squared. So 24 squared is 576. So O minus E squared divided by expected is now this divided by expected. So that's basically gives us 20.571. Now we just need to calculate the chi-squared as the sum of these two 20.571. That gives us 41.14. So that's how simple it is. So now we see that this is clearly larger than our cutoff value, and consequently it exceeds the cutoff value. Thereby the p-value is smaller than our alpha 5%. Consequently, we can assume that there's an association between time of the year and the probability to become an elite youth soccer player. So we're rejecting our null hypothesis. So do we think that is true? That's a whole different conversation piece, right? So this is statistically, if you approach this analysis in that shape or fashion, it seemed to hold statistically true. I would argue that it's not necessarily the light exposure time to the mother or factors of that kind that will give us this balance of youth soccer player and their birth months. I would think there's some confounding and some bias that is happening that is just not accounted for. But that's a different conversation, please. But yeah, on paper, this is to be rejected. So if we are looking now at Norton and Heinzen's computations, they found the same result. They also see that this is exceeded. So this is how you would essentially need to look at this data. So you have your threshold of 3.841, and you have your calculated chi-squared of 41. So this is exceeding your critical threshold, therefore you're rejecting the null hypothesis. But now it's getting a little bit more interesting. So that was simple, right? Are there any questions to the goodness of fit? I think that couldn't be any simpler, right? So now the test for independence is a little bit more involved. It's not complicated, but it's more involved. So you have now two nominal variables, which I do like this example quite a lot that Norton and Heinzen have chosen for this, and you will see why. So first of all, 6 steps of hypothesis testing. We identify populations, distribution assumptions, hypothesis, characteristics of the comparison distribution, critical values, calculation, and decision. So your comparison distribution is a chi-squared distribution, we know that, and the chi-squared for independence because we have 2 nominal variables. 17.2 is the following example. And it's a very neat example because it's environmentally conscious, but also economically conscious. Because let's assume we're running a nationwide coffee company, and we're paying a lot of money for trash, but we're getting, I don't know, we get a tax break for producing more recycling. It's cheaper to have recycling rather than trash. So we want to minimize the amount of trash we're producing. Now we're observing that most of our customers, they're trashing their cups after they drink their coffee. So we want to find a way, an intervention, to convince our customers to recycle the cup rather than trashing it. How could you do that? You play a psychological trick. You put the name of the customer on the cup, which is done quite frequently in nationwide coffee companies. So you could test whether this intervention indeed leads to more customers recycling their cup rather than trashing it by doing a small little randomized controlled experiment. And you're doing that by basically assigning 53 of your customers to a group where you put a sticker on the cup with their name written on it. Or alternatively, you take a sticker, and this is where it's becoming smart psychologically, with the name incorrectly spelled on it. Or thirdly, you don't put any label at all. These are the 3 groups we're essentially looking at. So the spelling of the name on the cup is the independent variable. These are the 3 levels of the independent variable, versus the dependent variable is your actual outcome. So this is what you're observing. You're observing whether customers trashing or recycling their cup. So you assign 53 people to one group. And I'm just going briefly through that, because if you're facing a question like that on the quiz, you gotta extract that information out of the question, right? So if you read it through, so you have, of those 159 people were randomly assigned to one of 3 groups. And that was a real research study of note. Of those participants, 53 were given a paper cup of which their name was spelled correctly. So that is a total of 53. Out of those 53, only 25 chose to recycle. So these are these 25. The resultant difference here is 28. So 53 is 28 plus 25. Then you have 53, only 13 was an incorrectly spelled name printed on it. Recycled it was 40 trashed it. And now you had those with no name on it, 14 people trashed it, whereas 14 recycled, 39 trashed it. So this gives us a total, a so-called marginal total, and I'm flagging this name because that's a technical term. It's a marginal total that adds up to the allocation to the respective groups. So that's random allocation to either of these groups. So that's balance between all three groups. And then you basically, you see whether there's a difference between these groups. And this is basically what drives our decision, whether there's an association with recycling your cup and printing a correct name on it or not. And the marginal totals are important on this quantification because this is your denominator. So marginal total here is the sum of these three entries. And what we see here is the shocking truth that not many individuals recycle the paper cup. What do we also see? We see that there seems to be less recycling, and there seems to be quite some difference in terms of recycling as per the spelling of the name. And this is this association we want to test now statistically. And this is done with a chi-square. So if we are now thinking about this in more detail, so we have the chi-squared, we have our formula right here. So we know that observed, so this data we have already, right? So then we have our trashed group. So now we've just brought it in a long format. Remember how I always talk about it. So this format is called, this is a contingency table, where basically you follow column and corresponds with the respective row. That is the cell count for that individual that meets these criteria, or this group of individuals. If you bring it in a long format, you're stretching it out and transposing it. So now you have, what's important when you do that is that you keep the labeling and you make sure that each of these rows has the correct label with it. Otherwise you get confused later on. So now this is our observed group. So this is what we have observed, carried over and transposed from our contingency table. If you were to quantify now expected, and this is where it's getting tricky. So you want to know now what would need to be the count in each of these groups if there were no association between the dependent variable and the independent variable. How could you do that? You know that the outcome that was observed is basically 52 in the recycling group and 107 in the trash group. So the dependent variable is always column, because the independent variable is organized as the rows. So you have total for each of your outcome levels. So you know it was 52 in the recycling group. If you would assume that your independent variable has no effect on the independent variable, that the independent variable has no effect on the dependent variable, there would need to be an equal and even distribution amongst all three levels of your independent variable. And the way you would quantify this is basically taking the total and dividing it by 3, because you have 3 groups. And that's how you get an even distribution amongst these 3 groups. So that's 17.33. So that's your expected count. That's what you would expect that count to be if you extracted 52 paper cups from your recycling. And you're now checking, okay, so is there name on it or not? But you basically, you would under null hypothesis, it should be 17 cups from each of these groups. So in the same fashion, you will do that for trash. So you do 107 divided by 3. That gives you 35.66. And that essentially is your expected count. It's as simple. So now the same concept applies now than earlier. So basically you're calculating observed minus expected. Now next you need observed minus expected squared, which is this squared. And now lastly, you just need to do observed minus expected squared divided by expected. And this is this divided by this. That's how simple it is. It looks more complicated than it actually is. And now we have a chi-squared to calculate, which is just the sum of these. And that's sum of these 6 entries. So we have a chi-squared of 7.6. So chi-squared of 7.6 is now larger or smaller than our cutoff value. So if we do degree of freedom row with 3 rows, 3 minus 1 is 3 minus 1 is 2. DF column is 2 minus 1, that's 1. So we have degrees of freedom. So we have degrees of freedom of 2. So if we were to look this up on our chi-square table, we have degrees of freedom of 2, an alpha level of 5%. Our critical value is 5.99. So EF X2 is 2, and critical value is 5.99. So consequently, we see that the chi-squared is exceeding our critical value, therefore we reject the null. And that's how simple it is. So the null hypothesis here was that there's no association between our dependent variable and the probability of trashing or recycling and our independent variable of having a name on it or an incorrect name or no name at all. So now that's the null hypothesis. Under the null hypothesis, we'll say we null hypothesize that there's no association between dependent and independent variable. So now we're rejecting that and we're saying there is an association. We don't know what it is, but there is an association in that data. And this is all that we can conclude at this point. For all further aspects, we need to quantify probabilities. So we need to dig a little deeper into this data. So we looked at observed, expected, that calculation we did. So we see here unimodal right skewed distribution, distribution. We see here the cutoff 5.99, and we see the actual chi-squared exceeding this. So based on that, you can also quantify the standardized residuals, and that's one way to basically indicate which one of those is basically different. So you can do this calculation. This is usually, so basically you have observed minus expected divided by standard error. We will do this on the lab day. You will not need to know how to do that on the quiz. So these are the adjusted residuals. You're quantifying based on the overall difference. You quantify the variability of the actual observed from the expected. And that's how you get the adjusted residuals. And so firstly, you want to quantify an effect size. The effect size is done here with a Kramers V or phi. And that is calculated by calculating the square root, Kramers V, is square root of the chi-squared divided by 159, which is our total sample size, right? Multiplied by our degrees of freedom, which is 2. Gives us a phi of 0.15. Putting the formula on the side. So square root of n18, which is our chi-squared, divided by 159 for our entire sample size, divided by, multiplied by our degrees of freedom. So now this would then follow conventions. And the conventions here with a degree of freedom of 2 is essentially 0.15. We're falling here, it's not even close to medium. It's basically a small effect size that we're seeing, but there is an effect size involved that is significant. So now we want to quantify this a little bit in more detail. And the way you would do this in more detail is by quantifying the actual probabilities of each of your cells. Bless you. So, bless you. You're quantifying the probabilities in each of your cells in reference to the marginal total of each of your levels of the independent variable. So what does this mean? So you're basically now calculating, let's copy this whole table over. That we don't need. That we don't need. So what you're essentially doing is you're calculating now, instead of this, you're calculating now the probability of being in one particular cell in reference to the total of that independent variable. So observed recycling and a correctly spelled name divided by your marginal total gives you a probability of being in this group if you had a correctly spelled name on it. So this is your probability. So now if I do the same exercise now with trash, it's 28 divided by 53. That gives us 53%. So this is basically how you would quantify this. Now you can just pull this formula down. And you get here already a little bit of an idea what those associations are. So this is, if you have a proportion of a count, remember probabilities, you have trials and you have success over trials. Let's assume recycling is success. And you have 53 trials and you have 25 successes. That gives you a 47% probability of that cup being recycled when the name was spelled correctly. Conversely, if there's no name on it, you have a 26 probability of recycling when there's no name. So now translating this into, well, let's first graphically depict it because it's an interesting way of depicting this. So you just have to select the entire table. You go on insert, and there's the bar signal right here. And you just create a 2D bar chart. Basically, will automatically arrange these in the same format. So this is basically, these are your probabilities. So you're comparing the probabilities between these three groups that are organized here in rows. And so now these probabilities, you could hypothetically, following the law of large numbers, extrapolate to a much larger population. We said we're a nationwide coffee company, right? So if we're producing, that's not just 159 individuals. If we're serving, let's say, 10,000 individuals, that's a lot of paper cups. And we're saving money with every cup that is being recycled, we're saving money. So these exercises are quite informative on many levels, let alone the ecological impact that this basically makes by saving the environment and go greener. So these probabilities can be quantified and then depicted as bar charts. I highly recommend to always use bar charts. We had the conversation in chapter 4 about don't use pie charts. No matter how tempting it is, just don't. Although you see them, you keep on seeing them. Impossible. But yeah, okay, so we have now probabilities for each of our cells. What we want to do next is we want to compare these probabilities. And Norn and Heinzen basically have this. Okay, so that's the bar chart. That's the bar chart with only one group. And so they're alluding at the last slide to the so-called relative risk. I personally believe there should also be a lecture on its own right, because relative risk is an extremely important parameter. It's virtually the whole world of epidemiology evolves around relative risks and risk determination. So basically, when you have a group that has a probability and you can quantify a probability of a certain outcome that is binary in nature, be it death, hospitalization, trashing a paper cut, whatever that binary outcome is, it's either yes or no. You can quantify this outcome using a risk determination, a risk of an event to occur over not occurring. And this risk can be quantified for each group. And to compare the risk of different groups, you basically need to have some way to quantify a comparative metric. And that comparative metric is the relative risk or relative likelihood. So it's basically nothing else but creating a ratio between the risk in one group compared to the risk of the other group. So if we want to do this exercise now, risk, no name versus correct name, is as simple as, let's assume the outcome to be that cup ending up in the trash. So let's assume this as the adverse outcome that we do not want to happen. So the desired outcome is recycling. So we're taking this as a risk that this cup ends up in the trash. So that risk here is 74%. So this essentially can be quantified as 74% divided by the risk of that cup ending up in the trash when it has a correctly spelled name. And that risk ratio is then 1.39. Now, what does this mean? The interpretation of this risk ratio would be that the risk of a cup with no name ending up in the trash is 1.4 times the risk of that cup ending up in the trash when the name is correctly spelled. So everything greater than 1 will indicate a higher risk. Everything smaller than 1 will indicate a lower risk. And that's important for the interpretation. You could also interpret it as that one group having a 40% higher risk compared to the other group. 40% increased risk. But this is not to be confused with the so-called risk difference, because you can also calculate the risk difference, which essentially is that group minus that group. And the risk difference would be 20% increased risk compared to the other group. So this is risk difference and risk ratio. Now you can use it in the same format. And this is now, you have numerator. That is basically your group of interest compared to a denominator, quote unquote, reference group. And that reference group is actually, that needs to be carefully chosen. Well, so is the numerator group, so that the group of interest. But if you compare now risk ratio, correct name versus incorrect or no name, then you would basically calculate your risk ratio as equals the sum of the respective groups here. So that would be the numerator is no name divided by no name divided by 53 divided by correctly spelled ink wrong way around. Okay. My bad. So we want to create the group of interest. So we are concerned correct name versus incorrect or no name. So we are comparing now the sum. So is correctly spelled name. No, we don't need the sum here. Correctly spelled name divided by sum of these two. So here we get, no, that's, yeah. So now we're looking at it from the other way around. So now we took the risk ratio of correct name as compared to correctly spelled name or no name. And now note that this is now smaller than 1. So there's actually a benefit of writing a name on it, which is basically 0.35 times that of having an incorrect name or no name. So that's now you're changing the angle. So the numerator determines the group of interest, and the denominator is basically determining the reference group. So depending on how you define those, that will drive what the risk ratio will look like for you. Good. Any questions to any of this so far? Okay, let's quickly go back. Let's just walk you again through this example. So make sure that you know how to extract information from the question. So you will need to quantify the respective groups. You will know how to extract the respective group. Make sure that you know what the total number, total count in the respective group is at each level of the independent variable. Always arrange contingency table with the dependent variable as the columns, the independent variables and the levels of this variable as the rows. Fill out that table based on the information you extract from that question. Calculate the marginal totals. I cannot emphasize this enough because that kind of gives you a self-check of what the count in the respective group is. Then basically take these observed entries, bring them in a long format, and think about how to quantify your expected count. The expected count is basically calculated as the marginal total divided by the number of groups, the number of levels of the independent variable. So under the, well, you basically pursue to fill them out as if the null hypothesis were true. That means that there's an even distribution amongst all levels of the independent variable. The next calculates the difference between observed and expected. Square this difference and divide that squared difference by the expected count. Sum this up and you're coming to the chi-square. You will then test this against the critical value that you have read from the chi-squared table. You're following along the degrees of freedom all the way down until you found the degrees of freedom that you have quantified for your contingency table. Degrees of freedom for row is basically the number of rows minus 1. Degrees of freedom for column is number of columns minus 1. And the chi-squared is the product of these two. You multiply them. That gives you the respective critical value from the chi-squared table, and you're rejecting the null if the chi-squared is exceeding that critical value. Next, calculate Kramers V or phi, the effect size, which is basically a square root of chi squared divided by the sample size of the overall contingency table. So all the entries, so that's 159, multiplied by your degrees of freedom chi squared. Gets you then a value that you compare against the convention. It's a table in your PowerPoint presentation. You can next calculate your conditional probabilities, which are basically the probabilities of an outcome occurring in the respective group defined by the level of the independent variable. And based on that, you can then essentially create graphs, this one. And you can utilize these probabilities to calculate risk ratios or risk differences. So relative risk is something that may come your way on the quiz questions to calculate that. Keep in mind that you have a clear vision which risk ratio you want to calculate. So the numerator needs to be the group of interest, whereas the reference level is the one, so either labeled as control group or the group without the disease or the group, I don't know what the question could be. But basically be aware which one is the group of interest which you want to put in reference to your reference group.
What is the risk difference?
The risk difference is another way. It's another metric to compare risks against each other. I'm just for the sake of completeness, I've added it. So you will only deal with risk ratio in the quizzes. Don't worry. It's always the more common one. It's easier to interpret and it's the most commonly used risk comparison metric. It's basically, yes.
Or do you want the risk ratio to be greater than 1? But that's only if your group of interest is like you were talking before, like no matter what, we want more people to recycle. So like in the case where the risk ratio had the recycling in the numerator, then you would want it to be greater than, like less than 0, right?
Exactly. That is the good, that is a $1 million question, because the group of interest and the reference group determines in which direction your risk ratio is going, right?
Yeah.
So whatever your outcome is, whatever you're interested in, you can look at this from different angles. If you're interested, what makes people recycling? Then you can basically define everything based on the recycling. You can compare recycling, the preferred outcome, in reference to trashing them, because you have put them as a relative term by calculating probability. So you can compare either probability. And the way you're arranging numerator and denominator, and this is why I keep on repeating that, the way you arrange numerator and denominator will drive your interpretation. So if you're saying, if I write my name correctly, or I write anybody's customer's names correctly on a paper cup, they are XYZ more times more likely to recycle as compared to that individual which did not have a name on it. Would be here the question. Or you can rearrange it according to your interpretation. So that's why risk ratio is very versatile too. But yeah, so basically based on this relative frequency, you can assume that there's a 1.4 times risk to trash a paper cup if it doesn't have a name on it. So that's the numerator. Alternatively, you have a 0.4 times improved risk to see this in the trash if you have the name on it. So that's the other way around, right? And then it's further determined, and that's also in terms of interpretation. If you extend the denominator, which I have done here, basically take an incorrect spelled name or no name, that becomes then your reference group. So you're bulking this together and you're saying, so this is the risk I'm comparing this to. Make sense? All right. Any other questions? Well, if not, we're done early. Have a nice evening. I'll see you on Wednesday.